my great pleasure to introduce you Dr. Mike Alexander. Mike and I have actually been working on a number of different projects over the last 3 to 4 years. Mike has kind of gotten roped into helping ecologists and fisheries scientists look at the effects of climate change on different fisheries. So we've done a number of projects using the output from global climate models to project the effects on things like you've probably never heard of, like the fish cusk, the Atlantic croaker, which is not an obscure basin in the Atlantic that you've never heard of, it's a fish. And we're working on some projects on river herring and American lobster. So we've been doing this collaboration, and I've taught Michael maybe a little bit about fish, and he's taught me a lot about atmospheric science and how to appropriately use output from global climate models. So I've learned so much from him. So I'm really looking forward to hearing his talk today, which is actually different from the talks that I usually hear him give, where he's explaining to fishery scientists or ecologists or even policymakers and managers on what the output from global climate models means and how to use it. So he's very patient with us, and he does a great job explaining it. So I'm really looking forward to hearing his talk on some of his other research. So to give you a little bit of background on Mike, for those of you that don't know him, he's from New York, so we're taking advantage of him being able to attend some business meetings here and at NOAA GFGL, as well as visiting some family back in New York. So he went to Cornell University, got his Bachelor's of Science there in atmospheric science. And then he did his master's and PhD in meteorology at the University of Wisconsin-Madison. After that, he was a research associate at the Cooperative Institute for Research in Environmental Science at the University of Colorado. And since 1999, he has been a meteorologist at NOAA Earth System Research Laboratory, where he's the lead scientist on a lot of different projects in the Climate Diagnostic Center. So today he's going to talk to you about moisture sources for extreme precipitation in the U.S. intermountain West.
Thanks, Janet. So yeah, it's nice to officially, can everybody hear me okay? To officially visit Stony Brook. I grew up in Queens, and so I feel like I'm back on my home turf a little bit. We used to go fishing not too far from here. So it's nice to formally visit and meet with folks here. So today I'd like to talk about kind of a different project for me also. A lot of my work is in kind of air-sea interaction, and we've started working with the Bureau of Reclamation, who is in the western United States, controls the dams, how much water to store over winter and when to release the water. They're also interested in long-term changes or long-term estimating long-term processes that could cause extreme events, because every 5 years or so they reevaluate their dams for safety purposes. Do they have to change their procedures, or would they have to increase the height of the dams or something like that? So this work has gone on to kind of start to address one aspect of those questions. And in the discussion that we were having with the Bureau of Reclamation, we were talking about they have dams, say, in places like Idaho or Arizona, which are generally dry, but can occasionally get very strong flooding. And some of the suggestion is, well, what is about the atmospheric conditions? How does the moisture get there? How does it get to these places that are usually dry? So that's what I'll talk about today. These are my colleagues who are all at the University of Colorado. So Jamie Scott, Justin Swales, Mimi Hughes, Kelly Mahoney, Joseph Barsugli, and Kathy Smith. Okay, so a phenomena that's been known about for quite a while is what's been termed, say, starting 20 years ago as atmospheric rivers by Reginald New, a famous climate scientist, is that during storms, you have ahead of the cold front, there can be long plumes of moisture. So this is a satellite picture of the integrated water vapor throughout the atmospheric column. And you can see that this plume of moisture extends all the way from the subtropics and tropics up towards the west coast of the United States. And what's shown in color here are cases where there was very heavy precipitation. So in this case, in these stations, it was the maximum precipitation ever recorded at those weather stations. There's also other colors that generally this particular atmospheric river led to a 1 in 100-year case of precipitation at some of these stations. So there's been people in our group who have studied these from observations and have studied both the large-scale circulation that goes with these. So generally there's a low and a cold front, and this is the moisture transport or moisture conveyor belt ahead of the cold front. But also how that can create very heavy precipitation in the Sierra Mountains, or when they go further north in the Cascades, or along the coastal mountains. So we want to go beyond that in terms of understanding how this moisture penetrates inland. So these are two cases. This was from a picture from a very strong flood in Arizona in January of 2010. And this is just a picture of one of the dams in the interior west, in this case in Idaho. So the river would have passed through here, and the dam extends far back, and then the watershed for this dam would be further west in Idaho. So the hypothesis is that when you have flow over mountains, so say over the Sierras, the air rises and cools, and so it can't hold as much moisture, so the moisture falls out as rain or snow. So this is classic orographic precipitation. So how does it get past those mountain ranges for when you have an intense precipitation event? How does it get, say, past the Sierras? So do the air parcels, do they take unique pathways, say go through gaps in the mountains, or are they able to go over the mountains if there's enough moisture? So that's kind of the question we're going to be addressing. So we're going to use two different methods to look at this problem. One of them is what's been termed backward trajectories. So you start at a location in space and time, and then from the three-dimensional wind field, you go backwards in time to see where that air parcel came from. So in this case, we're going to look at a station when there was very heavy precipitation at a station. We'll use the grid points in reanalysis. In this case, the climate forecast system reanalysis, which extends from 1979 to, in this case, 2011 that we're using. And we'll use the three-dimensional wind fields from that reanalysis to go back in time and make these trajectories. The other method we'll use is empirical orthogonal functions, or EOFs. So they're a way of looking at patterns, and in this case we're going to apply the EOF analysis to the integrated water vapor transport, which is we're looking at the magnitude of this transport. So throughout the entire column, sort of the winds multiplied by the moisture. And we'll also use this CFSR data set, which has a nominal resolution of about 40 kilometers. So it's much higher resolution than the earlier reanalysis that maybe people have worked with. We're going to focus on winter because that's when these synoptic systems, these atmospheric rivers, are strongest. Okay, so these are some examples of the back trajectories, in this case, computed for regions in southern Idaho. So the dam I showed before was sort of in this region near Boise. And these are on 4 different days. Each of these is a different day that happened to have quite a bit of precipitation, had a very strong precipitation event. And so then you're looking at the paths of the moisture, in this case going backwards in time, and you can see that they came out from over the Pacific and before reaching here. But there's different ways they could get there. Some seem to come across Oregon, others came north from California and then across northern Nevada. These particular trajectories suggest that the air associated with a heavy event came all the way from the southwest, sort of from the Los Angeles area and then north. And here is sort of a mix in the case where some kind of moves slowly, kind of trapped over the California Valley, Central Valley before moving up towards Idaho. So these are some example trajectories.
So what are the different colors?
Oh, I'm sorry. Yeah, so the different colors are elevation. So this is the yellow means that it's close to, it's at 1,000 millibars, so basically close to the ocean surface. And as you go to the cooler colors, you're going higher up in the atmosphere or to lower pressure. So, for example, these yellow ones here would be near the sea surface, and then they still have to go up some to go over the mountains, or at least the lower part of the mountains here. So that's why the colors get lighter. And you can also see the background topography. So it's very complicated in the western United States. Here's the Sierra Mountains up through here, and then the Cascades extend through here. This is the Columbia River Valley. This is the Snake River Plain here. So the mountain ranges are very complex, and the Rocky Mountains consist of all kinds of smaller ranges angled at different angles.
Excuse me, so you start at certain elevation? Or
Yes, so that's a good point. So we will start at basically between 50 and 100 millibars above the surface, so which is a pressure that's fairly close to the surface, so it would be sort of near the top of the boundary layer in the lower troposphere. We chose that level because the moisture tends to be greater near the surface. We wanted to be above the boundary layer, so we right above the surface, so the trajectories didn't run into the surface as we calculated them going back towards the ocean. Okay, so we're gonna use this trajectory analysis, and we're gonna conduct it for 6 regions, which were kind of subjectively chosen throughout this intermountain west. And we kind of used a number of factors. Did they have an adequate number of stations? We try to distinguish between areas that we thought would be grouped together, where the moisture parcels would come from, where there was dams of interest from reclamation, where dams were located, and so on. So we're going to we computed a fair number of trajectories so we could get an overall feel, not just a case on 1 or 2 days. So this is how we went about doing that. We computed trajectories for the top 150 events in terms of their 24-hour precipitation. So this is based on station data, and I'll show the stations in a minute. And then we're going to start the trajectories at the 4 CFSR grid points that are closest to that station or surround that station. So we started the trajectories between 50 and 100 millibars above the surface, or hectopascals above the surface. And we're doing every 50 millibar increment. So for example, if the surface pressure was like 827, we would be between 50 and 100 above that, so we would be like 750 is where we would start. So, and then we're doing this 4 times per day. So we have 150 unique events. We have the 4 grid points around the station, and then we have 4 times per day at one level, so that we're doing over a whole a whole region where we calculate 2,400 trajectories. Okay, so here are our regions. There's 6 of them. This color didn't work out very good, but there's basically one in Washington State and northern Idaho. There's one in Oregon and southern Idaho, Nevada, Utah, Colorado, Southern California, and Arizona and New Mexico. So this is just showing where the continental divide is, so that's kind of sort of setting the eastern side of where our regions are. And we wanted to be past where the major mountain ranges are, which are shown in this line here. So there's essentially the Cascades, the Sierras, and then the mountains that extend down Baja California, which are sometimes called the Peninsula Mountains. And each one of these little dots here, each one of those is a station that recorded precipitation. Okay, so what's shown on the left here is the absolute maximum at a station, and the color scales at the bottom in terms of millimeters of precipitation in a day. And so if the color ranges up to maybe 175 millimeters, which is a lot of precipitation in a day. And so this is giving an indication of where the events are mainly coming from. If there's an open circle, then it's indicating that that particular station didn't contribute, wasn't in the top 150. So for example, there's a rise in the kind of the edge of the Colorado Plateau here called the Mogollon Rim, and a lot of the heavy precipitations in Arizona happen in this region. And then what's shown on the right is just the percentage of the number of 150 events that are happening at that particular station. So in a few cases, you might get 10% of that 150 events happened at an individual station, probably one that's very close to the mountains where a lot of the precipitation falls, the local mountains. Okay, so our main tool that we're going to use is we're essentially going to count these trajectories. So we're going to count the endpoints of the trajectories as a function of time for the different regions. And so these counts will give us an idea of where the trajectories pass through. So this is an example of a count map that I'll be showing. So this is showing the number of trajectories. So the yellows are greater. In this case, there was 300 points, and then as you get to these sort of lighter greens, there's less trajectories. So the trajectories, took various routes from the Pacific and came to different areas. In this case, this is for our kind of Washington and northern Idaho region. The other way I'll be presenting the data is by showing a cross-section. So the cross-section will be along this black line, and it's along the ridge of the mountain ranges throughout the west. And so that will be presenting essentially the counts in a given area as a function of height. So you can see, where that air came from. Was it in a gap, or was it higher up in the mountain? Okay, so I'm going to go through each of the 6 regions, and so this is the count map for the Washington and northern Idaho region, and then this is the cross section over here. So you can see that for this area, we're using all counts for all days going back as far as 5 days. So while the trajectories are backwards in time, then if you think about the air moving, it's coming this way, it's coming in off the Pacific. And in this case, a lot of the air is moving up the Columbia River Valley, which is located here between Washington and Oregon, and then it would be moving into our target region here. And this would be the accompanying cross-section. And so this 45 north is basically here. So this is the gap in the mountains, this notch in the mountains. So this is suggesting that during these heavy precipitation days, And when we look at the largest number of trajectories, the majority of them are coming through this direction and coming through the Columbia River Gap and then on into Washington and Idaho. If one then goes to look at the next region further south in Oregon and southern Idaho, you can see that some of the higher values of count maps, you can see air, some of it is able to cross the Cascades. There's also a very interesting route here where there's higher counts over kind of the Central Valley of California and then extending to the north. And these lines here are showing the topography. So where there's, it could be hard to see, but the highest Sierra mountains, are many of them over 10,000 feet, are located here. And then there's a gap in the mountains to the north of those high Sierras in northern California. And so it's possible for the air to move, go around the northern end of the mountains and then come on up into Idaho. And you can even see higher counts that basically are follow this Snake River plain. So the air parcels are able to come through here and then move through this lower elevation, and probably bringing heavy precipitation to places like these mountains, the Salmon Mountains and so on here in kind of south central Idaho. And this is the accompanying count map, a cross section of that. So these higher counts are coming through at least this area here. So there's our very high Sierras, and then a fair number of these trajectories are passing to the north of the high Sierras. Okay, so for going through some of these other regions, we go through a little quicker. So this is for the Nevada area, and the high Sierras are here. And you can see there's sort of two pathways to reach Nevada, that both to the north and to the south of the highest mountains. And these are coming in at fairly high levels. So they probably, even though they're going over the passes are high. So they probably still have to drop quite a bit of their moisture before moving into Nevada. So, this is very strong deserts. The mountains there are contributing to the fact that there's not incredibly heavy precipitation in that area, but there's still ways for moisture to make it in there.
Do you make any attempt to see what the rain fallout is on these paths leading to your areas of study?
Yeah, so we haven't broken it out by day. At this point, we're kind of looking for the general climatological conditions, but this map is showing the absolute maximum at a station, and you can see that in Nevada itself, most of them are kind of light green, which is on the lower end of the scale there. Say as compared to like there's some yellow and kind of reddish values here in parts of Idaho. So in those cases, you can indicate that you can get a much heavier rain. Okay, so I think we made it here. So this is the pathway into our Utah and Colorado area. There's heavy precipitation events here on the western side of the Wasatch Mountains, which kind of run north-south through Utah. And again, an interesting pathway that's going down. In this case, the back trajectories would have gone past in this case, the southern part of the Sierras, and then through the gap. There's gaps in the mountains here, and then originating out over the Pacific. And this is the cross-section map that goes along with that. Finally, our two southernmost regions. So here's the Southern California area, and also for New Mexico and Arizona. And so here you can see that to reach this area, there's sort of a path that's kind of along the border. There's a higher count along the border, and then there's some that cross Baja, mid to lower Baja. And Baja has, the highest mountains in Baja are kind of in the northern part, and then as you go further south, they drop off quite a bit. So it's just that a pathway to bring moisture in here into to Arizona and bring those heavy events to this Mogollon Rim can be through this, going all the way south and then crossing Baja and then coming up through the Gulf of California and then into Arizona. Okay, so what I presented so far is trying to count these trajectories that occur when there's very heavy precipitation events. But a question arises is, are these pathways unique? Could you just get it on any given day during winter? Could the air traverse those same routes that I just showed? So to address those questions, we computed, again, used back trajectories, but we examined it randomly. So if a station had a top event, we could randomly pick between those stations and then randomly pick days. So we're just trying to pick, given any kind of day that might happen in winter at one of these stations, and then calculate the trajectories there, and then we're going to compare them to the extreme cases that I just showed before. Okay, so this is an example of these count maps and cross sections. Again, for our Washington, northern Idaho region and our Oregon, southern Idaho region. And you can see that to first order, if you can remember what I showed a few pictures ago, that they don't look that different. Okay, that there's still air coming. The back trajectory would have come from the Pacific. There's still a bunch that are coming up the Columbia River Valley. And this is the case for Idaho. There's still some from California, although some coming kind of through the northern route. And so this is just to remind, this is just a comparison. This was the count map for the randomly generated cases, and this is the count map for the extreme cases. And so you have to kind of maybe zeroth order, they're similar. But if you look more closely, that one can start to see differences. For example, more of them remain in the region of question, so the region of interest. So that's suggesting that they're probably not propagating as fast back out of the region, and I'll show some more of that a little bit later. Also, that there's the random ones seem to be coming over a bigger spread and further north compared to the ones during extreme cases. So to see these changes better, I'm going to show difference maps. Okay, so the difference maps will be extreme minus random. Okay, so where one sees blue colors, that means that there was more, in the extreme cases, more came from that. There was higher counts, and more came from that direction in the extreme cases compared to the random. And where there's red, it's the reverse. There's more counts, more trajectories in the random cases. So here you could clearly see that in the region itself, there's many more random cases. So suggesting that they're being counted more often. Right around, they're not moving as fast, or in that case, they're probably in extreme cases is stronger, rapidly moving moist air into that region. They're also tending to come from further north. So there's kind of blue colors here and red colors further north. So in this case, instead of more trajectories coming up from this direction, when you get a heavy case, more actually probably with cooler, drier air moving over the Columbia River Valley and then down into southern Idaho and eastern Oregon. And these are the cross sections, and that's showing that too. For example, here for southern Idaho, more of the air was actually coming up through that gap, through the Columbia River gap, and less were coming from that California area. And another factor to notice is that if you look, there's more red colors up high. The bluer colors tend to be lower. So that's suggesting as the air is moving from east to west, it's at higher elevations, which tend to be drier. So the air can come from a wider spread, come at higher elevations over the mountains, and then drop down into the target region we're looking at. So I'll just go through those other sets of regions quickly, and the same kind of pattern emerges. So redder meaning more counts for the random cases in the target area to start with, and more red at higher elevations. The air is coming from higher up where it would be drier. It's not a moist source near the surface. And they're coming from further north in the random cases and further south, the blue colors, in the extreme cases. And so if one thinks about an atmospheric river, they tend to come from, you would have a low pressure, you would have a strong cold front, you would have the flow from the southwest, bringing more moist air near the surface. And so these kind of analysis are kind of, the count maps are kind of bearing that picture out. Okay, for the same for these final two regions. So I'd like to present this second method to try and confirm some of the things that we're trying to glean from the count maps. And the second method is this pattern-based method called empirical orthogonal functions. So we're taking these three pictures here are the first, the second, and the third empirical orthogonal function, or EOF, of the integrated water vapor transport. Okay. And we've done two things before calculating this EOF. We're excluding over ocean areas, so we're only looking over land, and we've normalized the variance by kind of the local standard deviation of this IVT, integrated vapor transport, because the vapor transport is greatest over the ocean and greatest over to the west of the mountains. But since we're interested more in interior, we're doing these two things so we can see where the patterns are greatest when we're focusing on this intermountain west region. So the leading pattern, and that explains about 27% of the variance, shows what would be vapor transport anomalies of one sign, pretty much throughout the west, with the maximum kind of over southwest Idaho. The second one, which also explains a lot of the variance, 23%, has a dipole pattern. So if it was of this sign, it would be positive for vapor transport here, and anomalies here, and negative here. So this is actually the magnitude of the vapor transport. And then the third EOF has a 3-cell pattern with anomalies of the same sign along the northern and southern boundaries of the U.S. Okay, so we're going to use these patterns, and associated with them would be the time series, or the principal component. And so we're going to look at the principal component and construct composites, essentially when these patterns would have a lot of amplitude in the actual data. So the PC has a large value at a given time. We're going to use that in our composite. So we're choosing this would have a distribution. We're choosing the top 1%. So the top 1% would be about 250 cases. We're using every 6 hours. So 256 hour periods when this pattern would be very strong. We're going to use both the upper and lower value of this one, because if it's positive, it implies a lot of moisture transport into Arizona, and then the large negative phase would imply a lot of moisture transport here along the boundary. And for the third one, we've tried to decide if this is actually a real pattern when you do EOF analysis. Sometimes as you go deeper down, the patterns, they may not represent real conditions. They may more just try to be a statistical way of maximizing variance. And it turns out we can focus on the southern area, which seems to be associated with the synoptic conditions of like cutoff lows and moving in. So I'll show those three composites next. Okay, so this is a composite of the top 1% or essentially 250 cases that are averaged together of various meteorological quantities. Okay, so this is the integrated water vapor transport, so this is the magnitude. This is the vector, so this is this is the magnitude. The color scaling also shows the magnitude, so it shows the actual direction of the vapor transport. We have two estimates of precipitation. One is from CFSR itself, so the reanalysis we're using, and then we've also gone to a higher resolution data set that just covers the United States, and they've extended up into the Columbia River Basin in southern Canada. So we have our two estimates of precipitation. This is 500 hectopascals circulation, and this is the specific humidity, or a measure of moisture. Okay, so we did the EOF based on this quantity, and so it's not surprising that you're recovering that pattern, but with the composites, we're not normalizing and we're including ocean values. So you can see that there's large water vapor transport in towards the western United States. The vectors are pointing in this direction. It's kind of moving on shore throughout California and into Oregon. And then there's pathways that showed up in kind of when we looked at our regional trajectory analysis. So there's stronger transport into, in this case from California and then into southern Idaho, and then from the Oregon case also into, in this case, northern Idaho. So, I'm sorry, go ahead.
So Mike, so 1% of the PC1 value, so like how many cases are going to these composites?
Yeah, so these are taken from years 1979 to 2010 in winter values, and so 1% corresponds to about 250 winter days, or 6-hour periods. So a large number. Okay, so this is a combination of both the moisture, which we've shown here. So you can see this is a kind of our atmospheric river. Here it is, kind of taking this, unique pathway coming in over California, kind of turning at the California boundary and going into with maximum moisture over southern Idaho. This is the IVT circulation. So it's going along with, it's both a combination of this moisture and then the integrated circulation, which is probably nicely shown by the 500 millibars height. So you have, in this case, a high pressure ridge to the south and a trough to the north and west. And so the flow, the geostrophic flow would be from out over the ocean following the contours. And then would be strongest where the gradient is strongest. So this is kind of the setup. You would have synoptically you would have a front, you'd have a strong trough and ridge pattern and strong flow that's coming on shore. And then the mountain gaps are kind of so here's the fire hose, and then the mountain gaps are acting to direct where that moisture is going to go. And then here's our precipitation. So of course you're lighting up with the moisture coming this way, part of the Sierras and Cascades, but you're also lighting up heavy precipitation in the mountains of Idaho, both kind of central Idaho and northern Idaho. And actually reanalysis doesn't do a bad job of that. We didn't really know how well reanalysis did, and this is kind of a 16th degree reconstruction of the precipitation that takes into account the topography and so on. So yeah, you can see that in both cases it's showing that this is a way to get heavy precipitation into Idaho. Okay, this is our composite based on the second principal component, the second EOF. Remember, for the positive phase, that kind of showed a large IVT here in Arizona in the southwest U.S. So you're recovering that as part of your composites. You can see the vector aspect of this integrated water vapor transport, the moisture extending out across Baja California and out kind of to the tropical, subtropical Pacific. This is a circulation, so a low and the ridge would be a little bit further east here. And again, suggestive of very strong southwest flow. And this is the precipitation. So this is also a way to bring precipitation to the Sierras. But now you're getting quite a bit along this Mogollon Rim, this edge of the Colorado Plateau here in Arizona, and also parts of Utah and Colorado. So this is the opposite phase. So if I was showing the positive phase of that principal component, this is the composite based on the negative phase. And so that would be associated with lots of IVT along the northern tier states, along the border. And so one sees that. And then again, but still that moisture extends from the south and west, and then would be transported up and then into these northern tier states, and leading to heavy precipitation here in Washington. But now you're really picking up the northern part of Idaho. So depending again where your ridge and trough sets up, and your synoptic circulation, pumping this moisture up from the subtropics, and then finding ways, probably here again through part through this Columbia River Valley to reach Idaho. Okay, and this is the last one I'll show. This is kind of a modified version based on the third EOF, and the circulation that it picks up is essentially a cutoff low, which is kind of a fairly well-known situation. Sometimes you'll have a trough throughout the West, and a low pressure center would cut off from the main trough. And so we think that this is a real feature. The analysis is picking up a real feature of the circulation. You can see here the moisture has a very southerly path, IVT, and that moisture itself. So it's crossing southern Baja and then coming on up into to Arizona and New Mexico. So these cutoffs, although they're not as strong as the full trough, because they can tap this very warm, moist air, they can be very effective at bringing moisture and then precip to Arizona and New Mexico. Okay, so everything I've been showing up to this point has been kind of at zero lag. The composites were at the time that a maximum occurred, but we could also look a couple days before and a couple days after. So this is the zero lag. This is we would have seen this picture before. In this case, I'm showing for this top, the first EOF, or the first the composites based off the first principal component, and then one can go back 1 day before and 2 days before, and it's showing that indeed that the vapor transport was from further out in the Pacific. As you go back in time or going forward in time, the moisture would have originated here and then propagated, towards the coast and then onshore, and then this is 1 day later where it kind of breaks up as it moves into the intermountain west. Okay, so in summary and discussion, we've kind of used two different methods, sort of this back trajectory method and the EOF analysis to try and identify where the moisture sources are coming from. So it's pretty clear that that there are indeed pathways that for very extreme events that the moisture it really can't really go over the very high Sierras, and it finds its way through lower elevation gaps in the Cascades or the Sierras or the mountains of Baja California, and depending on where the target region is, where that heavy precipitation is going to fall out. However, we saw that there can be all kinds of flow of air through the gaps too. It doesn't have to be laden with moisture that, dry air or cold air could also use the gaps. And so what it is sort of a combination of two things. It's a combination of, are you setting up with very strong moisture transport from the southwest funneled at where that gap is to push the moisture through the gap and then give you the heavy precip event. There can be 2 or more pathways to a given region. So for example, for the Washington area, it looks like it can come up the Columbia River Valley, or some cases could go through that kind of California path, so to the north of the Sierras, and then in this case go almost due north up into very northern Idaho. Also, a single path can traverse more than one of the regions. So an example would be some of the area that kind of came in over the southern border between the U.S. and Canada, was a way to bring heavy precipitation to parts of Arizona and parts of Utah and parts of Colorado. So the station locations we used they're mainly in like valleys. So they may miss extreme events, which are often happen at higher elevations. So that could affect where we're doing our back trajectories from. So our back trajectory methods may miss, at least so far, we may have missed some areas or some mountain ranges. For example, if you've ever skied in Colorado, there's a famous place called Steamboat, which gets a ton of snow. It's in northern Colorado. And we didn't really identify a pathway through there, probably because the stations there at lower elevation, other stations were saying, we had more rainfall or snowfall. So basically using different stations or higher resolution data or methods for not subjectively kind of picking these regions, we may be able to better quantify these pathways, do a better job defining than sort of our first cut here. So I have a few slides showing like an individual case study of an event that happened in Arizona, but it's about 10 to 1, and I imagine people are hungry, so I'll stop here and take questions. Yes?
Those EPOF for the vapor transport anomalies, there was also a mean field in there, wasn't there?
Those were the mean field was subtracted out.
Right, I wondered what the mean field looked like. Was it really large compared to the anomaly fields?
That's a good question. We have the mean field, but I don't have a mental picture of it in my head. I imagine the maximum, you would see some transport coming onshore, where there would be a mean trough, and so maybe the maximum would be kind of in Central California for the mean case. But we should actually go back and look at that, what the mean looks like.
So how this EOF moves the way to El Nino? Any relationship at all?
Yeah, so we haven't really identified that directly. I mean, certainly El Nino affects these ridge trough patterns. So, for example, something like this here would El Nino affects the large scale circulation, and so the kind of the dominant El Nino pattern would be kind of for a low pressure here to the south of Alaska, and so that in that case it may favor a certain route, but it would be good to, we could go back, for example, from these composites and look to see if they occur more during El Nino events.
Your mode 1 does look like this big illusion load. So very much like an El Nino.
That's correct. Yeah. It might be a little bit further off, but yes, this could be a. So the classic El Nino pattern would have a kind of a low here, a ridge that would be kind of more here, and then a low off the map. So it would be interesting to look at El Nino both now the the classical El Nino and the Central Pacific El Nino to see if there's differences in these things.
Yeah, I had the same question, but so your composite analysis is based on the daily time series of EUF. Is
That's
that
correct.
So did you check, and that is top 1%?
That's correct.
Did you check if there is some interannual variation of this PC time series?
So we just grabbed it from whenever it occurred. So we did not try and look for, did it change from year to year and things like that. And that's something that could be done and then related to El Nino, PDO, things like that. So it would be interesting to do that kind of analysis. Yes?
Have you considered the seasonal cycle?
So far, we're just using from October to March. We're using everything throughout the winter. So these river phenomena are pretty much a winter phenomena. Because in summer, a lot of the precipitation is much more local and the water gets recycled from where it fell out. But we haven't, it would be good to look for it from, I would say, from fall through spring and see if there's differences, say, in fall versus midwinter versus spring. It could be that some of these, for example, these patterns may be seasonally dependent too. You know, this perhaps I'm just giving, maybe this is more, you know, kind of a midwinter situation. So we haven't tried to do that, but that would be a good thing.
But even October and March can be different amounts.
Oh, absolutely, absolutely. So, I guess there's trade-offs between if you narrow your season more, you would miss more kind of possibilities of defining events. So as our first cut, we basically chose the cold season, but I think we have enough data that we could separate out and look for differences between, you know, fall, midwinter, and late winter. So maybe, you know, we could do it monthly or maybe bi-monthly would be a way to look at some of these structures. That's on our, I would say that's on our to-do list pretty soon. Is there a question in the back?
I'm sorry, I missed the topic, how you define the IBT values. So these are integrated references, right?
Yes.
What is included in this function?
So it's basically from the surface to the, I think we went up to 300 millibars, and it's the wind, and so it's V times Q and U times Q.
So only water vapor is included. How about when we have precipitations, we have usually different hydrometric species, and water vapor is just one part. All the other species will also be transporting with the wind, but probably with different speeds.
Yeah, I don't have a feel for out of the total amount of water, how much is carried by actual like liquid water. My, you know, large scale meteorology event guess would be that would be a small fraction of the total water, but that could be wrong. Also, something like the reanalysis, you know, I guess you could calculate the liquid water, but from the, I'm not quite sure that we would have access to that, and I don't know if I would trust it. But it would actually be interesting if one could get it from estimates from satellite data or something like that to see about transport of, you know, ice crystals or liquid water as part of this as part of this process.
You try to do a forward trajectory.
People have done forward trajectories, so essentially you could pick areas here and see where
they end up.
You would probably want to do a large volume and more than we have done. I think the concept of the back trajectory was in part where we started from, that the people who controlled the dam said we want to understand what caused precipitation here, where did it come from? But in terms of understanding the broad synoptics, one And I think there are studies out there where people have generated large volumes of trajectories and then analyzed what parts of the tropics.
Well, I would think that if the forward and the backward are different, they'll give you a lot of insights about what really happens. If they are similar, that would be trivial, but they are actually quite different.
Yeah, I guess one could try it from the forward ones. One could maybe try and do some kind of cluster or EOF analysis also to see how they would group, and perhaps we've missed something from just doing it kind of this regional backward trajectory method. Yes.
Yeah, actually, you would get different answers because what's called air mass transformations, different latent heating profiles. You wouldn't get the same answer forward or back, I don't think, given the different latent heating profiles. But my question was, the trajectories are interesting. I just wonder, this is a classic orographic precip problem where the question is how much moisture is making it over. So have you or anyone calculated the moisture budget? I mean, where in orographic precip we call it like a precipitation efficiency, you know, and Ron Smith and others have looked at this with isotopes and others, where the question is how much, in your trajectories, how much moisture flux is actually going through the gap versus up and over. And so you can actually calculate in a box, right, the moisture convergence or sort or region and where it's coming from in that. So one thing I was thinking of with the reanalysis data might be tough because you have data assimilation cycling and the moisture is not conserved, you know, every 6 hours because you're getting observations. So to do that with reanalysis might be tough if you actually want to get a real budget. But I think someone could use model or some kind of gridded, you know, case study prediction. But
I mean, I'm trying to think of, so the thing I didn't show is we did basically a one case study of a detailed understanding of a case in Arizona where both observation based and based on WRF. So the WRF is a regional atmospheric model and was run at 3 kilometers, and it seemed to match the precip from WRF seemed to match the actual precip. So then one could go into WRF and do a budget.
I guess the reason why I'm asking is, I mean, you can get heavy precip 2 ways. You can have a moderate amount of moisture upstream that could go through gaps and not be depleted by the mountains. Or you could just have an incredible amount of moisture source upstream with one of these rivers, and it could still make it over the Sierras and still end up with, you know, maybe you only have 30 or 40% of the moisture left, but it's still more than you would end up with most other cases because of the huge source upstream for those particular events. So I'm still trying to sort out, and almost reflected in your trajectories. There is some suggestion through the gaps, but there's a lot of other trajectories going up and over, even for those big cases. So the question is, what fraction of the moisture is actually coming through the gap versus up and over? And
I agree. What was shown here was what we call qualitative. Some aspects of the trajectories too is that you could be in different parts of the storm. So some of the ones that go over that do go over like the Cascades, which aren't nearly as high as the Sierras, could be they're in the dry sector of the storm. So not every trajectory is necessarily directly tied to every precip. And they can be sensitive to the level that one starts at.
I also kind of follow what Brian just said. It looked to me that's missing information. I try to draw an analogy with fish recruitment. Basically, you not only try to see the trajectory, you also try to know the age of say, the lobby, right, as it goes. And so in your case, you have the trajectory, but you also have the moisture content, which is critical. But your analysis is kind of basically just looking at the trajectory, and then you, of course, looking at the big pictures. So somehow, there's this another half information which is not really in the analysis, the trajectory analysis. It's probably critical. That's what Brian just said.
So I guess
how the moisture sort of, you know, each trajectory actually has a moisture information to go with it. Right?
Sorry. So the trajectories are, they're just an air parcel. We're not modeling an individual moisture parcel. There are people who are basically doing that within like a model like CAM5. So they're actually tracking moisture parcels, and then one could see one could look at a moisture parcel or maybe a group of them and see where they did they come off the ocean here and move. And I think one open question with this is, so you look at that beautiful satellite picture, and you have this long plume of moisture, and is the parcel like coming off the surface here and going this way, or is it essentially goes her way, it rains out, and then other moisture comes off the so it's rather than a river, it's more like a grasshopper, right? going like that. The first part is I agree that there's more work to be done in terms of a quantitative budget of understanding this, and can we give a good amount of say that for something here for rain or snowstorms here in winter, is it 60% through the gaps and 40% over the mountains, which would be an excellent thing. Yes.
This is more for clarification. When you were doing the backward trajectory, you decided to put the level from 50 to 100 hectopascal above the surface. And I'm wondering whether the raining clouds would be at that level. Why didn't you choose the height of the raining clouds?
Yeah, so for the station that for that analysis we started with station data, and so the stations are just reporting precipitation at the ground. I guess from the CFSR analysis we could look for the level of maximum moisture transport and start to trajectories there. So that would be a way to go about it. Some of the choice of how we came to that was based on the basic. If you look at a basic moisture profile, most of it is kind of in the lower atmosphere, and then as you go further up, the amount of moisture the air can hold decreases. So the choice of that was based on that. But we could be more quantitative from the CFSR and look for the start to trajectory at the maximum moisture level.
Yeah, because I think if you start slow, you're kind of biasing your trajectory to favor the lower parts, the lower passes where there are gaps.
Right. Yeah, so I guess some of if you start higher up, then I guess we could do a comparison starting higher up. We did look at some of the higher trajectories, and as you go higher up, the air can come from many more different directions and stuff. So we if you're associated with a storm, and the air can come from many different ways. It could come, a dry air could come in as well. So we kind of felt it was better to be lowered to the surface where more of the moisture would be just in a general sense. But that's true. Maybe we biased it to we're looking lower so that more of the air is going to come through the gaps.
Yeah, I'm not an atmospheric scientist, but I don't know where exactly the raining clouds be at. Roughly.
Yeah. So probably neither does reanalysis. But it might have a handle on where the moisture is.
Right.
Where the moisture is maximum. So that's a good point. We could base the trajectories on where the maximum at that time was in the climate.
For those trajectories be connected to rivers, or your trajectories be connected to atmosphere rivers following?
I think that probably much of the precipitation in the western winter is associated with atmospheric rivers, and this is kind of a picture like this, I would say, is very much like an atmospheric river. So an individual case would be, probably much narrower and concentrated. And then, it's coming here, and then it's, okay, we're arguing that a fair bit is kind of coming through these gaps, but it's possible that some of it is also going up and over the mountains. I do know that there is one study by John Brutz, who's at University of Utah, that kind of did the atmospheric river perspective. So looked at the defined atmospheric rivers, and that study also found that the high Sierras were definitely a block to these atmospheric rivers, and also that this kind of pathway over southern Baja and into Arizona, they also identified that as a pathway to the rivers.
Well, I guess we're gonna have lunch with Mike later, and you can